All right, these are the notes for section 5.4. We are solving right triangles, and we're going to be doing some applications of right triangles or some word problems. This first part of our notes is dealing with significant figures. So just sort of a word, often in mathematics and often mathematics teachers, when they give you numbers, we sort of pretend that they're exact. So for example, exact numbers sometimes, like there's 23 students in my second period class, or there are exactly 100 centimeters in 1 meter. So those are exact values. But often things are measured, and so if I said I'm 73 inches tall, well, I'm not exactly 73 inches. I've measured it, and my measurement isn't exact, but it's accurate to the 1 whole inch. To the nearest whole inch, I'm 73 inches. Okay. The classroom is 29.5 feet wide, so this is measured to the nearest tenth of a foot. Okay. So when we deal with calculations using measurements, things that we've measured, we have to, and in science more often than in math, we concern ourselves with significant digits. So let's go through some examples and what the significant digits are as a general rule of thumb for how many significant digits should be in our answer. Now, often we're going to tell you round your answer to the nearest blah, blah, blah. And in that case, then don't really worry about significant figures. But this is a good rule of thumb, especially in science classes. So for each of these numbers, let's come up with the number of significant figures. All right, so pause the video. Put down what you think each of these measures, the number of significant figures. So for example, the first one is 3 significant figures. Pause the video, do it for all of them, and then unpause the video and we'll discuss. All right, the second one is also 3 significant digits. This one seems like it's 9. Like if you type that into your calculator, the calculator would just treat that as 19, right? So it seems like 19. But the fact that I put those zeros, the only reason I would put those zeros in is if I knew the measurement to that accuracy. So this is going to be 4. All right, this one is going to be 3. Again, in math, we treat 6.40 the same as 6.4, but in science, it would not be treated like that. All right, this one would be just 1, right? 3 is there. The decimal place is telling us what value that 3 has. It's not 3, but 3/100ths. But the other zeros in that case are not significant. This one is 2. This one is 2 as well. Now you need those zeros there to make that 9-2 really mean 9,200, okay? And there are some science teachers might argue like some of these are ambiguous. I think if you put a decimal point there, then I think some science teachers would probably say, oh, okay, that decimal point is now telling us that these are significant, in which case you would have 4. I think science teachers probably have a better grasp of this. We don't use significant figures that often in mathematics. Okay, again, we pretend like everything's an exact value. Or the next one, 51 inches, 51 degrees, 30 minutes. This is going to be 3 for the 5 and the 1 and the 3. The next one will be 4. This one will be 5. This one will be 1, 2, 3, 4, 5 as well. And then this one will be 3. Okay, so the rule that we use in science is that you're doing some calculations with some measurements. Your answer cannot be any more accurate than the least accurate measurement that you used in the calculation. So that's kind of the general rule. So if if you're multiplying something that has 4 significant figures by something that has 2 significant figures, your answer should not have any more than 2 significant figures. And, again, science teachers probably have more specific, those are just kind of the general rules. For us, if we, use this kind of idea as a general rule for what to round to, how many significant digits should be in your answers. But more often than not, in this class, we'll probably tell you what to round to. Okay. Find all angle measures and all 3 side lengths of each of the triangles. Note the right angle measure is exactly 90. So if it's 90 degrees, that's the one case where it's almost like infinitely many. It's an exact value, so we don't talk about significant figures in that case, or we think about it as infinitely many significant digits. All right, so in the first triangle, we are trying to find A and B, and then this measure of this angle here. So probably the easiest thing to do is find the angle first. So theta, that's equal to, all 3 angles sum to 180. This one is 90 exactly. So really these two are complementary. So we can just subtract this one from 90. And that gives us 54.9 degrees. Okay. A lot of times people will say 90 plus 35.1. Take that sum, subtract it from 180. But we can just take the 90 right out of it, and these two things are complementary, though. They sum to 90. Okay. Let's look at finding B. And so if we want to find B first, there's no reason. Well, you could find A first if you want, but find B. And so I'm going to use cosine because this angle, 35.1, B, and 21 are related using cosine. So the cosine of 35.1 degrees is equal to the adjacent, which is B, over 21. So we would simply multiply both sides by 21. We make sure that our calculator is in degrees. Make sure that the degrees is showing up, the D in your calculator showing up. So we do 21 times the cosine of 35.1. So we say B is equal to 21, multiply both sides by 21, times the cosine of 35.1 degrees, and that would be roughly 17. And so since this measurement is 2 units, probably makes sense to leave that one as 17 meters. Is it exactly 17 meters? Probably not. I can actually do it in my calculator here. 21 times the cosine. Oh, hang on. Let me double check that my calculator is in degrees. Yeah, it is. Okay, so 21 cosine of 35.1. And yeah, so it's 17. And again, depending on what I would ask you to round to, but 17.18, maybe 0.18. Or if you said 17.2, the one measure is 21. Now, again, in mathematics, we often think of that as being an exact value, but we know it can't be. We've measured it, and so we know it to the nearest whole unit. But we just don't, in mathematics, we just don't feel right saying that's 17 because that sounds like it's exactly 17. Okay, what else? All right, we want to find A, so we could use the sign if we wanted, or we could revert back to the Pythagorean theorem. We know that A would be equal to the square root of 21 squared minus 17, and then depending on, again, so if I use 17, I'll get a different value than if I did 17.18. Okay, so, and then that's squared. All right, so let's see, we have the square root of 21 squared minus 17.18, and then we'll square that too. And so this gives us A of 12.08 if we're doing it to the nearest hundredths meters. Okay. Now we don't generally have to put down that that C, we call this angle C, that's always going to be our 90 degrees. So we don't have to put down 90 degrees. We know that that is a right angle. All right. So we looked for the three things that we're missing, right? We know the right angle. We know this acute angle. We know one length at the side. We can find the rest of the three things. Our three things are the other angle and the two legs in this case. All right, moving on to B. On B, the angle is given to us in degrees and minutes. So when we go and ask for beta, we should leave our answer also in degrees and minutes. So again, we would just subtract that from 90. So beta would be equal to 27 degrees, 48 minutes, right? So we want degrees and minutes, so that's the angle we're looking for. And then what else? We know, again, we don't need to find angle C. We know it's a right angle. We're looking for the hypotenuse C and this length that we're calling D. All right, so we can do C, and we can do that with sine. So we can do, let's use the sine of the original angle. So we do sine of 62 degrees, 12 minutes is equal to, again, it's sine, so it's the opposite over the hypotenuse. So 17.25 over C. We do a little algebra and we rearrange that. C is equal to, we kind of flip-flop the sign in the C, so C's by itself and upstairs, 17.25 divided by the sine of 62 degrees. Now we would want to change the 12 minutes into degrees as well by dividing that by 60. But ultimately, when you do that, you would get something like 19.50. The units here, this unit is foot, so we have feet. All right, so that's side C. And then we can just use the Pythagorean theorem. We could, again, use another sign. We could use the cosine of this angle is D, adjacent over hypotenuse. But let's just find D using the Pythagorean theorem. So it's the hypotenuse, which we just found, 19.50 squared plus 17.25 squared, and then we'll of course take the square root of that, right? So then that's 9.09 feet. And again, I'm rounding to the nearest hundredths. Technically, everything seems to have 4 significant figures, so I might put 9.093 for that. Okay, and so that is the 3 missing pieces. All right, and then on this last one, C, same kind of thing. In this case, we want to find the angles. They didn't give us either of the angles. They gave us the 2 lengths. This time we're going to use the inverse tangent, is what we learned last time. So theta, this angle down here, is going to be, if we do the tangent of theta, that's this over this, the opposite over hypotenuse. So theta is equal to the inverse tangent of that ratio, 5.361 over 6.215, and that is 40.78 degrees. And then, of course, we can just subtract that from 90 to get our alpha. We don't have to use a trig ratio. That's 49.22 degrees. right? So we have our two angles. Now we need to find this opposite side. Again, Pythagorean theorem probably works best. That is x, the hypotenuse, is the square root of 5.361 squared plus 6.215 squared. And so x is equal to 8.208 meters, no, inches, units on this. The double, that looks like seconds if it was an angle, but it's inches because it's a length. Okay. All right, let's look at D now. Solve triangle ABC. Again, same thing. They just didn't draw us a picture this time. So they told us C is a 90-degree angle. They give us the length, the measure of angle A and the length of side B. Let's draw that in. So this will be C, opposite the right angle. They give us angle A is 24 degrees, 24.0 degrees. And then this side, opposite angle B, this is angle B up here. Opposite that is this one, and that is 23.45 meters. All right, so we need to find A, and we need to find this angle up here, angle B. All right, so angle B, that's easy enough to find. It's just the complement of A. So we can say measure of angle B, or we could just say capital B, either way, is 66.0 degrees. Okay, and then we just need to find C and A. So we can use either one we want. Let's take the 24 and let's use tangent. So that would be the tangent of 24 degrees, 24.0 degrees, is equal to A over side B, 23.45. Okay, so A is going to be equal to 23.45 times the tangent of 24. And we get 10.4. All right, and what are the units? That's meters. Okay, and then since we know two of the three sides of the right triangle, we can simply use the Pythagorean theorem. C would be equal to the square root of let's see, the thing they gave us, which was 23.45 squared plus 10.4 squared. When we add those squares up and we take the square root, we get 25.7 meters for C. Okay, so again, all those A, B, C, D there, that was all about what we call solving a right triangle. It means finding the side lengths and the angle measure for each unknown angle. Basically, they have to give us three pieces of information about the triangle, and then we can solve for the other three. All right, bearings now. So bearings are like little vectors, and we have a couple ways of indicating them. So first, we start with either the north or the south. So we're on the north end or we're on the south end of sort of this compass. And then we want to figure out how to draw the ray ends. The ray starts at the origin where the north, south, east, west all meet. And then we want to draw a ray out from there. In this case, we're starting on the north, and then we're going towards the east 30 degrees. So we're going 30 degrees in that direction, but we're starting on the north. And so something like, oh, I don't know, that maybe, where this would be 30 degrees in there. Okay, and so that drawing, that is the bearing. North, 30 degrees east. Okay, now, north, 75 degrees west. All right, so we're starting on the north, and then we're going over 75 degrees, something like that, where this is 75 degrees. All right, and so this is the bearing starting at the origin. It is sort of basically wherever you are, like you have a compass, and instead of walking north, you're going to walk in this direction 45 degrees, 75 degrees to the west from the north direction. Okay, so that's one way of doing bearings. And then another way of doing bearings. Well, let's finish this one, and I'll talk about it in the other direction. So, in other words, with these, the way of doing, there's two ways of doing it. In this way of doing it, you start with north or south first. So this one we're starting south. So like we're facing south, and then we're going towards the east 15 degrees. So that is 15 degrees, and the bearing means we're going in this direction. Okay, so if you were at this point and you had your compass, you would go and turn around so that you're facing north, facing south, and then you would go 15 degrees towards the east, and that's what this vector is the bearing, south 15 degrees east. Now, another way of doing this is to not give north and south and to just give a bearing. So, for example, if I wanted to describe this bearing, I could use this notation, but I could also just say 160, a bearing of 165 degrees. And that is telling me always then, if I don't use a north or south, I'm starting from the north and I'm going in the clockwise direction in order to get to this 165. It would end up being that same one. So think about how we would give this bearing in this other notation where we don't say north or south. All right, so we're starting at the north, and we want to say how many degrees that is. All right, so that coming from the north, again, our standard angle always starts on the x-axis, which would be like the east, but not here. We're starting on the north, and we go clockwise direction until we get to our bearing, and so that will be 285 degrees bearing. All right, so again, no north, no south, no east, no west. So if I just give you a bearing and then a degree number, that means start on the north, go clockwise until you hit 285 degrees. So that would be 270, and then this is what, 15 more degrees, so 285. Okay, so that's another way of doing bearings. Let's look at going in reverse now. If I give you a bearing, describe a bearing based on an angle. So this one is almost like in standard position. What would be the bearing? How would we describe the bearing in this case? So using our north, south, east, west, we would say, now we wouldn't go south. So we want to use the north or south, whichever one it's closest to. So this angle is the angle we want to call out. It's less than 90 degrees. If I were to say south and then so many degrees this way, that would be bigger than 90 degrees. So you want to pick the north or the south that is the closest. Does that make sense? So this one would be 65 degrees in here. So I could just call it 65 degrees without any north or south. Or in this case, I could call it north 65 degrees east. So either one of those is acceptable. Okay. So we want to figure out how to go do this one. Again, think about how many degrees are in here. If that's 75, this has got to be 15. So this will be south, and then 15 degrees to the west. All right. Now using our normal bearings, that means describe it from north. What would that be? without any north, south, east, west. So that's 15 more than 180. So that would be what, 195? So that would also be an acceptable bearing to describe that location or that vector. Okay. All right, and the next one, that's 5 degrees in there. So this one is closer, so we would say start with the south, then go towards the east, but how many degrees, right? So that would be 85 degrees. And then using the other type of bearing, we would want to describe that angle. And so say that bearing is 95 degrees bearing. Okay, so some of the homework will give you bearings without any east, west, north, or south. They'll just give you a bearing that's not standard, our standard angle. And also notice that going in the positive directions for bearing is almost like the same direction as going, well, not almost, it is, going in the same direction as a negative angle when we're talking about angles in standard position. So just kind of be aware of that. All right, let's look at example 3. A boat leaves a pier and travels 20.0 kilometers at a bearing of 35.0 degrees east, north, 35 degrees east, then turns to a bearing of south, 55 degrees east, and travels for another 50 kilometers. How far is the boat from the end of the original pier from where it left? All right, so let's draw a picture for this. We're on, the first bearing is north, 35 degrees east. So let's draw an east, west, north, south, essentially a Cartesian coordinate system. And we're north 35 degrees east, so we're up here. Okay, and we travel 20 kilometers. And then at that point, we change direction. So we almost like superimpose another XY coordinate plane on there. And now we go south 55 degrees. Let me get rid of this 20 kilometers here. Let me put that up over here. So let's put 20 there. So it's kind of a little bit out of our way. And so now we want to go from north 55 degrees up. And so that will be something like that. And we go 50 kilometers in that direction. And then we want to know how far away are we from the pier where we started after we go 50. All right, so something kind of like this. And so we want to know that length. Well, now if we think about it, that was 35 degrees. So that would be also here, that's 35 degrees. And we already said that this, we know that is the 55 degrees. So that triangle, this big angle up in here, is a right angle. And it's the only way that we could really solve this at this point. We'll have, we can do more complicated bearing problems in later sections when we learn some more theorems. But for now, the resulting triangle has to be some sort of right triangle. And indeed, 35 and 55, that's a right angle up there. So what do we have? We have some sort of right triangle where this is 20, this is 50, and that's a right angle up in there. And so we want to find x. So we simply use the Pythagorean theorem. We know x is going to be the square root of, and x is the hypotenuse. So 20.0 squared plus 50.0 squared, and that ends up being about 53.85164 in our calculators. And so we say, well, we use 3 significant digits in these things, so it probably makes sense that we use 3 here. So 53.9 kilometers is how far the boat is at that moment from the original pier.